All right, next up we have Lav Varshney, who is an associate professor at the University of Illinois at Urbana-Champaign, with research interest in the areas of science and engineering of informational systems involving humans and machines.
Great. Thanks, Erica, and thanks, Venkat, for projecting my slides. I was having some trouble. I'm actually at the IEEE Symposium on Information Theory out in Athens, Greece, right now. So, uh, yeah, thanks for having me. So I'll jump right in and talk about how we're trying to model and measure scientific creativity. And as part of the grant, I'm working closely with James Evans, who's a sociologist at the University of Chicago. And I can tell you next slide. So, yep. And I'd stay on the previous. Yep. The one with, yep. Yeah, so I'm an information theorist, and that's why I'm here. And so we're trying to bring mathematical ideas together with kind of the more social and data-driven ideas that James works on. And I think that's been kind of a nice connection. We've actually done several papers in the past together, bringing our various expertise together, and we're excited to do that here. In addition to my university appointment, I also do some work at Brookhaven National Lab on AI for Science, and I'm also running a music company, which is called Kokri, which is designing methods for making creativity much easier for regular people. And so you'll see some of those ideas kind of woven through this talk. And James has a further affiliation at the Santa Fe Institute, and so you'll also see some elements of complex systems arising here. Okay, next. And just to briefly give you some background, I've been working in computational creativity for quite a while. And I think there's actually some nice potential intersections between scientific computational creativity and creativity in other fields. For example, more than a decade ago, I started and led the Chef Watson project at IBM, where we built an AI system that could generate flavorful and novel culinary recipes. So that's the food truck on the top left. We've been doing work in music again for several years, and you can see on the top right the Double Dutch Hip Hop Express bus. So that it's actually a converted school bus that's a music studio that we take around and help people compose new music. And another example is on the bottom left. So we designed an algorithm to generate novel formulations of concrete, which seems like it should be a problem that was solved, thousands of years ago. I'm here in Athens, and there's concrete buildings here, but actually we were able to develop formulations of concrete that have half the carbon emissions required as traditional concrete, and yet are just as strong. And as you may know, that's huge impacts, because 8% of global carbon emissions are due to concrete. So you can have that. It's the equivalent of removing all of aviation, for example. And this was poured in a big data center that Meta was building in northern Illinois, in DeKalb. So it's already been demonstrated in full deployment in one of these $1 billion plus data centers. Likewise, the culinary work has had kind of more than $100 million of impact, and a lot of the products you can buy in grocery stores, like McCormick's one mix spices, are designed using our technology. Right, so there's a lot of kind of interesting relationships among these different creative and scientific fields. And as we're trying to model and measure creativity, as part of the project, we're largely taking a domain agnostic view, and then we're trying to kind of make sure that things work for all the different scientific domains that people are working on. All right, next. Great. Just briefly to mention, James has also been working in computational creativity for quite a while, and especially on augmenting innovation and trying to move beyond human creativity towards AI creativity. Next. And he takes often a kind of systems view, thinking about the scientific system and its social aspects quite a bit, and how different representations flow into understanding and plans. And a lot of his work in the Knowledge Lab at UChicago is asking, how can we think better? Next. And yeah, he's been a big pioneer in the field of science and meta-knowledge, which again is very core to this question of trying to evaluate scientific creativity. Right, next. One other kind of super compelling area that James has been working on, and this is something I thought a lot about last year when I was serving at the White House. I was on leave to serve in the National Security Council. And James has been taking a scholarly view of it, is how different national innovation systems actually interact and uh, compete or collaborate, and how that leads to various notions of national competitiveness, which again I think is very critical in terms of creativity and its evaluation. Because if we can understand kind of the nature of innovation systems broadly as well as specific creative algorithms, I think that can help us be more creative. Okay, next. Next as well. Okay, so just to dig in a little bit more into what we're working on very specifically as part of the DARPA grant. Let me just back up to the 1950s and 1960s and the emergence of kind of systems theories broadly, whether it's information theory, control theory, theories in signal processing, and so on, in fault-tolerant computing as well. And what Peirce really argued is that what every engineer needs is a good set of limit theorems. And I very much kind of appreciate this point that as we're building these scientific creativity systems with AI, it's helpful to have a set of limit theorems. And they're useful for a variety of things. So next slide. Right, so fundamental limits are useful for at least four things in my mind. First, they establish the playing field in terms of which resources and performance criteria are fundamental and which are largely unimportant. So to take the previous example, like in robotics, it's useful to know kind of which resources in robotics are fundamental and which ones are largely unimportant. Like are decorations of the colors of the robot, perhaps not. And in terms of performance, maybe it's energy efficiency, maybe it's other notions of capability. Secondly, fundamental limits allow us to establish fundamental benchmarks in terms of evaluating progress. It allows us to have an absolute scale rather than only compared to previous scientific findings. It seems to me that it's much better to say that you're within 0.00045 dB of the best possible thing you could ever come up with, no matter how much cleverness the engineer or the AI is applying, rather than just saying it's twice as good as what the other guy did last year. Right. And so these fundamental benchmarks on an absolute scale are a second key thing that come out of fundamental limits. And then third is more of a sociological point. Once you know the limits, you can work hard to approach or achieve those limits. To take the information theory as the example, communication engineers worked for 60 or 70 years quite hard to achieve the Shannon limit. And if they didn't know what that limit was, maybe they wouldn't have worked so hard. And then finally, fourth, the fundamental limits actually help describe what an optimal system is. In delineating what's possible from impossible, one can actually provide insights into operating at that boundary. To take a thermodynamics example, the Carnot limit actually helps you think about how to design a good engine. So these are kind of four reasons why we care about limit theorems. And what we've been doing and are continuing to do through the project is establish such fundamental limits for creativity. Right, next. And again, just to emphasize the point, here are some examples of fundamental limits. So Carnot established the fundamental limits on the efficiency of engines, and engines like the diesel engine operating at high temperatures approach those limits. Claude Shannon established fundamental limits of communication in the presence of noise, and codes like low-density parity check codes and turbo codes approach those limits. And again, taking kind of robotics as an inspiration, for flying robots, Karaman and Frisoli established the fundamental speed limit of how fast drones can fly through forests without crashing. And again, if you operate Below that speed limit, you can actually fly infinitely without crashing. On the other hand, if you exceed that limit even a little bit, you'll crash infinitely often. Right, so all of these kind of fundamental limits are compelling because they provide design principles as well as establishing the playing field. Next. And one of the keys to establishing fundamental limits are actually to first define a closed deductive system. As the sociologist of science, Bruno Latour, described, Carnot's know-how is not about building a machine, but rather a diagram. This diagram is drawn in such a way that it allows one to move from one engine to any other, and indeed to non-existent engines simply drawn on paper. Real three-dimensional steam engines are interesting, but localized and cumbersome. Right, so we want to establish kind of a deductive system as well. Next. And Shannon himself, in the first paper on information theory, said that frequently messages have meaning. They refer to some physical or conceptual entity, but these semantic aspects of communication are irrelevant to the engineering problem. So he cast semantics out of the scope of communication theory and said everything within the block diagram of the communication system is what we care about, and what is outside we do not. Okay, next. Right, so let's try to do something similar for creativity. So creativity, as per psychologists of creativity, is said to be the generation of an artifact that's judged to be novel, and also to be appropriate, useful, or valuable by a suitably knowledgeable social group. Right, so how can we try to mathematize this? Right, next. So what we want to do is actually have a formalism for artifacts of creativity, like a robot, a notion of novelty, like how surprising it is, utility or functionality, in terms of its value in some sense. And we need some background knowledge to be able to characterize these things. Right, next. Right, so one way we can do this is we can think of combinatorial creativity, which actually captures nearly all creativity, where new ideas are constructed from components. And so we can think of an artifact as an unordered combinatorial object drawn from the power set of possible components omega. And then we can think of a known set or an inspiration set of things that are already created in the creative domain. And that is a subset of 2 to the 2 to the omega. So the set of things that artifacts that are already known. There's a non-negative novelty function that goes from artifacts and the inspiration set to the positive reals. So it's saying how novel is this new artifact given what we already knew. And one example of this is the Bayesian surprise. And then utility or functionality is also a non-negative function that maps from the artifacts to the positive reals. It measures kind of how good something is. And one can also extend that to be from 2 to the omega cross 2 to the 2 to the omega to the positive reals, because often the context matters. So what's already known actually influences how functionally useful something is. Okay, next. So as I said, one example of a novelty function is Bayesian surprise, which is a relative entropy between the conditional posteriors given the new idea and the prior beliefs. So if one computes the scale divergence, it actually captures very strongly how humans perceive novelty and where they pay attention. Right? So this would be kind of one example of a novelty function. Okay, next. In terms of utility functions, there's different approaches to this. Sometimes you might draw on existing scientific knowledge to define what utility is. For example, in materials, you might think about like Young's modulus. I mean, that seems like a nice measure of utility or functionality. Or for robots, maybe it is energy efficiency. Or for biological settings, it might be efficiency of doing cut and paste operations of DNA. But you can also perhaps learn these from data. So we further define trainable utility functions or Sobolev utility measures and for either discrete or continuous settings to restrict ourselves to things that can actually be learned from data. Right. So these are kind of other kind of wrinkles to the formulation. Okay, next. Okay, so now we have defined a notion of novelty, we've defined a notion of quality, we've defined artifacts, and we've defined knowledge. And we can use these to actually assert a novelty quality trade-off in creativity. So, for example, we might want to optimize surprise under a quality constraint. And we might do this in an expected sense. So we might maximize the expected novelty over the choice of a creativity algorithm, which I'll denote by P alpha, capital alpha of lowercase alpha, such that the expected quality is more than the constraint Q. Here we're thinking of creativity algorithms as stochastic sampling. So there is some stochastics to it. And that actually captures any creativity algorithm you can think of. Deterministic ones would just be degenerate versions of that. Okay, so this would be a reasonable notion of a novelty quality trade-off. And the interesting thing, if you go to the next slide, is that the expected Bayesian surprise is actually Shannon's mutual information. And so, in fact, the novelty quality trade-off is a flipped around version of Shannon's capacity cost function. So there's a very fundamental relationship between creativity on the one hand and communication or resolution of uncertainty on the other, which is quite interesting. And it also gives us a lot of machinery to actually characterize fundamental limits, because there's 80 years of information theory that we can draw. Next. And so we can compute these kinds of fundamental limits. We can compare those against what people have built. So we can see how human creativity stacks up against the fundamental limits. We can see how machine creativity stacks up against the fundamental limits and see how close we are to those fundamental limits. Right, so this is a core aspect of what we're working on, is computing these kinds of fundamental limits and then comparing from data how existing methods of creativity actually play out. Okay? And then it'll encourage people to work closer to those limits. Okay, next. Great, and in particular, we're drawing on kind of hypergraph models as well as part of the generative process to describe kind of what the nature of creativity is and how close that is to fundamental limits. Yeah, I won't go into the details of this, but you can think of a variety of generative models and see how close they get to fundamental limits. Okay, next. Okay, and further, as I was mentioning, just like in communications where Shannon's capacity achieving input distribution actually describes optimal codes, likewise, the extremal P alpha of alpha, this description of an optimal creativity algorithm actually describes what a good creativity algorithm should be. And so one can actually use that as an inspiration for building very practical creativity algorithms. And so that's, again, a very compelling aspect of modeling creativity in this way, is you get insight into designing good creativity algorithms. And that's another thing we're working on. Okay, next. Okay, so this is all good, but can fundamental limits change? And so again, let me take an example from communications. You would think that communication channels are fixed, when you talk on your cell phone. But actually, if you put your antenna on a drone or a robot or something, you can move it around and actually try to get a better channel, right? And so then the fundamental limits actually change. And so that's the other big piece of how we're thinking about modeling and measuring creativity. Because as you keep discovering new things, it actually changes the limits of creativity. Next. Right, so we can think of kind of considering expansion, so expanding the set of components to construct artifacts. For example, if you discover a new culinary ingredient, you have a whole set of new recipes you can make. But even more interestingly, you can expand the set of utilities that make up functionality, because functionality is not just a monolith. So when you want to build a good cell phone, you want good communication rates, but you also want good mobility and various other factors like energy efficiency. So there's a bunch of utilities, and you can think of new utilities that make up functionality that might emerge. Okay, so that's the other core piece of what we're thinking about as part of our research. Next. So in particular, there's compositional structures in terms of how things go together in terms of the ingredients. So this is super interesting that we're working on. And you can actually form kind of directed acyclic graphs of compositional structures of ingredients. Next. And there's often kind of this hierarchical way of thinking about it in terms of higher order assemblies and so on. Next. Which is what's even more interesting is that you can think about compositional structures for functions. There's actually often relationships and either logical relationships or statistical relationships among different notions of functionality. So if you knock out like one disease-related gene, that might impact other diseases as well. And there's complex functions like the efficacy of drugs is there's various things like water solubility and impact. And I mean, there's all kinds of things that are also related. So we're working on kind of how to incorporate these notions of compositional functions into our theories. Okay, next. Again, there's kind of these hierarchical questions, as I said, about toxicity, solubility, robustness, and so on. Okay, next. Right, so broadly speaking, we're really pursuing this question around multi-order creativity, how one can get novel structures, novel functions, and really see how that compares against what the best one can do, and how humans have been doing it and how AIs are about to do it. Okay. Next. Okay, and we're also doing a little bit of work on our own as part of the project in a biology setting, in plant biology. So we're helping some of our colleagues at Illinois come up with new experimental designs to optimize plants for a variety of functions like oil production and resilience to climate change. So we're super excited about all of these things, and I'll stop there.
Very fascinating talks. I have a quick question. So, I mean, I think your work is really elegant in your definitions. For instance, you had defined those information theoretic metrics, and I think you came up with the maximization of KL divergence and things like that, right?
Mm-hmm.
And intuitively, we understand that in many of our scientific problems, but in reality, how does one even define a probability distribution with any amount of confidence, right? It's our own description of the phenomena that is the most uncertain, right? Can you comment on that aspect?
Yeah. So as I briefly mentioned, like utility functions can be learned from data. So if one has trainable or kind of Sobolev utility functions, so that's kind of part of the challenge. And the other thing is, as I think everyone in the room realizes, supervised learning is largely useless for creativity, right? Because you never see the full things. If you've seen it, it's not creative anymore. So it's really about learning properties of components and their combining rules. And so that's kind of the core of that question around utility, around kind of probability distributions in the first place to measure novelty, for example. Again, we've largely been thinking about kind of empirical measures through the history of science. And so that's really the empirical distribution of what's been done before as the prior against which to compare the new things. And again, this kind of gets to the kind of like core philosophy of creativity. So philosophers of creativity often talk about H creativity versus P creativity. So H is kind of historical, again, comparing against all creativity that's ever been done in the history. On the other hand, P creativity is person specific or algorithm specific. And the hope is, so it's, I could come up with a peanut butter jelly sandwich and that might be new to me, but, everyone else has done it in history. And the hope is that algorithms can actually be as H creative as possible by drawing on the historical record and not just be P creative, just being novel to themselves.
Yeah, that makes sense. the other question I had in mind is it possible to use some of these kind of metrics to assess how creative or emergent or lack thereof, are some of these large language models, right? So there's a lot of discussion about emergence, and some people just say you just take a different metric and all that goes away. I
Yep.
think that would really help some of the characterizations.
Yeah, we've thought a lot about this. We haven't done any studies yet, but I'm quite confident it can be done. I had a paper in 2020, which was about explaining the outputs of LLMs, kind of using semantic networks, and I think that path can be extended to do these kind of creativity characterizations as well.
Yeah, that'll be really cool. I look forward to that.
Yep, sounds good.
Any other questions from?
Yeah, thanks, love. That was great.
Great. Yep, thanks everyone. And feel free to send me more questions. I know there's a bunch of students and postdocs in the audience, so just email me and I'm happy to talk more.
Yeah, thanks.